So far we have seen how to calculate a single spin in a magnetic field using the conventional wave functions as the formalism. But now we will see there are certain problems when we want to describe many spins, many identical spins, and that's what we will face now. We want to deal with many identical spins in NMR because in a typical NMR sample we have 10 to the 20 spins, and of course we cannot describe this with just a single spin usually. So dealing with many identical spins is an issue, and the problem originates actually from the phase factor. So spin states are only defined up to the phase phi, as we have seen. Spin states are only defined up to the phase phi, where any spin state will give the identical result. Any spin state psi prime, which is simply e to the I phi times the spin state psi. And why does this lead to a problem? Well, we look at two spins, for example. We have here spin one particle, one spin here. And that has the wave function psi1, which, for example, we describe as 1 over square root of 2, 1, 1. So that would be the x state. When we look at any expectation value, psi1, ix, psi1, then this simply will give the result 1/2, as you would like. But then there is a second spin here, spin 2, which, well, has the wave function psi2. And we say it's the same wave function, but has a phase. This phase is randomly distributed, so we have here e to the I pi, for example, over square root of 2 times 1, 1. That can be written as 1 over square root of 2 minus 1 minus 1. And again, when we apply here the expectation value, then we have psi2 ix, psi2 is simply 1/2, as we would expect. Even more so, we see like psi1 ix, psi2, we will result in having no interference, meaning the two spins are really treated separately, just as we want to have it. So everything seems fine. But now if we want to add up the two spins, we would like to add up the wave functions. And then we have a problem. Because when we add up psi1 plus psi2, which is equivalent to adding up psi1 plus psi2 in the cat form, then this is simply 1 over square root of 2, 1, 1, plus 1 over square root of 2 minus 1, minus 1. And that results in 0. So when we add up the two wave functions, we do not have anything anymore to describe on. This is a problem. And if we have 10 to the 20 spins, for sure we have random phases. We will end up with nothing in the end. So we have to find a formalism that describes these many spins without the phase factor playing this destructive role. So we take one step further and we go to the statistical operator P and if psi is just the vector C1, C2, then we know an expectation value for A is simply psi A psi equals C1 star C2 star times A11, A12, A21, A22 times C1, C2. And this equals simply C1 star C1 A11 plus C1 star C2 A12 plus C2 star C1 A21 plus C2 star C2 A22. Well, we now define the statistical operator P as the dyadic product of psi with itself. So it's psi ket times psi bra. And if you write this out, then, well, it's simply the column vector C1, C2 times the complex conjugate row vector C1 star, C2 star. And this gives the matrix C1, C1 star, C1, C2 star, C2, C1 star, and C2, C2 star. And if we now define a different scalar product for the matrices, then we can calculate any expectation value for A as the trace of the statistical operator P dagger times A. And this is then the sum over I, sum over J of P I J times A I J. And when we write it down, then this simply gives C1 times C1 star A11 plus C2 C1 star A12 plus C1 C2 star A21 plus C2 C2 star A22. And when we compare this result, then we see it is the same as what we got before. So we can do the expectation value. We just have a different way of calculating it here with a trace of the statistical operator times the desired operator A. But why do we do this? This is simply when we look now at an psi prime equals e to the I phi times psi, and we put this into the statistical operator, then we will find that psi prime times psi prime just is e to the I phi psi times psi e to the minus I phi. And because the e to the I phi is just a number, 1, so this is simply psi times psi. So P is independent of any phase factor e to the I phi. And this is a very important result, because with this operator now, we can describe many spins. But what does this statistical operator actually represent? How can we interpret the data? Well, we have the statistical operator P, psi, psi. And okay, I write down the coefficients again, C1, C1 star, C1, C2 star, C2, C1 star, C2, C2 star. And when we look at it now, then we see that the state alpha and beta, the two states are connected here with alpha bra and beta bra on the other side. So in the end, the coefficients of the statistical tensor directly give us the transition probabilities between the states. And therefore, it's natural that we also would like to pose a condition, which means that the sum over I and j of Pij should be 1, as it is the sum over all transitions possible. And of course, altogether, this should be 100% of all transitions happening, meaning that it is normalized to 1. So with these transition probabilities, we have to, of course, now to rewrite also the fundamental equations a bit. And so fundamental equation for spin is clearly the Schrödinger equation. So what we do now is we rewrite the Schrödinger equation. And this is simply, well, we know the conventional writings, d over dt psi equals minus I h psi without the h bar. And when we calculate this for the ket vector, we can also calculate it for the bra vector. This looks then slightly different. That is here psi bra equals plus I, because of the complex conjugate, times psi bra times h for the Hamiltonian. Now we can simply put these two results in and write the time derivative of the statistical operator P, which of course is d over dt times the dialectic product psi times psi. And now, using the product rule, we simply can write this is d over dt psi times psi plus psi ket times d over dt bra psi. So, and now we can put in the equations to the left, and we will end up with d over dt of p equals minus I times the Hamiltonian and psi times psi plus I psi ket psi times the Hamiltonian. And of course, we see directly that we have here the statistical operator again. So this is minus I Hamiltonian times P minus P Hamiltonian. And this is nothing else but the commutator of the Hamiltonian. With the statistical operator P. So this bracket here is the well-known commutator in quantum mechanics. So we now have this equation, and with this equation, of course, we will be looking for a solution. So again, we look at the easiest case, which is that for the Hamiltonian being piecewise constant, we find a solution which is P of t equals e to the minus iht times p0 times e to the iht, and add a quick proof, which simply means that we have d over dt of p of t is now d over dt e to the minus iht times p0, p of 0, e to the iht, plus the other terms of the product rule, which is e to the minus iht, now d over dt, p of 0, times e to the iht, plus e to the minus iht, p of 0, and now d over dt, e to the iht. When we look at these different terms, then we can see directly that P0, the derivative of P0 as being the initial state, so fixed state, that this is 0. And so we only need to consider the other terms. And so we have the derivative here is minus IH times e to the minus IHT, P of 0, e to the IHT. And then the last term would be e to the minus IHT, P of 0. And then it would be I times IH times the rest. But I write first e to the IHT times IH, using here the theorem that the matrix exponential of a matrix H has the same eigenvectors as the matrix itself. We can actually change the order of the two terms. So, and when we do this, then we simply see this is again P of t, this as well. So we can write it minus I as H P of t minus P of t times H. And this is nothing else but the commutator H with t. And that is what we wanted to prove. So indeed, we have a solution. We have now the initial statistical operator P surrounded by two matrix exponentials, e to the minus IHT and e to the IHT. And with this, we can calculate now spin properties. But how do operators look like? We now know already how to calculate time evolution, and actually how do the single operators look like. So we look at example operators, and we can simply calculate using the wave functions. So for example, x times x equals 1 over square root of 2, 1, 1 times 1 over square root of 2, 1, 1. And this results in 1/2 times the matrix filled with ones. And when we now deduce or separate out two matrices, then this is simply 1/2 times the unity matrix plus Ix. So, and continue now with the other operators. You can have minus x equal 1 over square root of 2, 1 minus 1 times 1 over square root of 2, 1 minus 1, and that is 1/2, 1 minus 1, minus 1, 1, as you can calculate easily. And this is again 1/2 times the unit matrix, and now minus Ix. So we get the result that in this case now, indeed, the wave function for x and minus x result in a matrix where the operator minus Ix is indeed having simply the opposite sign of the Ix operator. So I mean, really, we have now an opposite operator for opposite direction, which I think is quite nice. We simply do further matrices, and so we have the y operator, which then results with a similar calculation to 1/2 unity matrix plus Iy, and equally the minus y operator will result in 1/2 1 minus Iy. And we can look at the alpha state being 1, 0 times 1, 0. This is of course 1, 0, 0, 0. And we know this operator to be I alpha. And then the beta state is simply results in I beta. Now we have a closer look at the unity operators and what is their role. And as we are interested in time evolution of our spins, then we simply look with the unity matrix, and there we define the P prime of T being simply e to the minus I h t times now 1 plus some statistical operator P e to the I h t. And when we calculate this, we can simply separate the two elements, and this is e to the minus I h t times the unity matrix times e to the I h t times e to the minus I h t p e to the I h t. And there we see that this part here, because the unity operator commutes with all matrices, you simply see that this is again unity matrix. And so we end up with 1 plus e to the minus I h t times p times e to the I h t. And so the unity operator does not change under time evolution. And because of that, we simply, in the following, will neglect all these unity operators being present in the x and y operators and calculate only with the equivalent of the Pauli matrices here for this statistical operator P. But now we have this very nice statistical operator P, and how can we describe our many, many spins, 10 to the 20 spins with it? And there we have to go one step forward, and that leads us to then the spin density operator and spin density formalism. So the spin density operator we can introduce now with a spin ensemble. So an ensemble is defined simply as a collection of independent identical systems. And when we look at spins, then we have, of course, an ensemble of spins, so ensemble of identical spins. And then we simply can define here a spin density operator rho, which is the statistical operator P averaged over all spins, meaning this is the dyadic product psi, psi, and averaged over all spins, and this results in 1 over n times then psi 1 times psi 1 plus psi 2 times psi 2 plus many other spins plus psi n times psi n, where n is simply the number of molecules with identical spins, or we can also call it the number of systems. And with this spin density operator, we can rewrite the Schrödinger equation equivalent, and this is then rho dot as the time derivative equals minus I commutator h with rho. And this equation has a name. It's called the Liouville von Neumann equation. And that is the central equation usually for describing spins in NMR spectroscopy. And of course, this then has the solution rho of t for a piecewise constant Hamiltonian, which is written as e to the minus I h t rho 0 times e to the I h t, where of course rho 0 depends on boundary conditions that we apply. And so for getting to know how this operator really works and to get a first impression yourself how calculations are being done, I would like you to do an example calculation as an exercise. And so we pretty much have our Hamiltonian, as previously noted, as omega 0 times Iz. We have our initial spin density function, rho of 0, being Ix. And now we should be able to calculate with the formula given the expectation values for Ix, Iy, and Iz. Where, of course, Ix, for example, is calculated, as mentioned before, and as the trace of Ix dagger times rho of t. And rho of t simply is e to the minus IHT times rho of 0 times e to the IHT. And just, if you don't know, the trace of a matrix M is simply the trace of the broad. We have here the diagonal M elements M11, M22, and up to MNN for an n by n matrix with other values around. But the trace is simply the sum over all diagonal elements I. So I think you tried to calculate all the expectation values, and I'm sure you got to the right result. And I simply want to give you a solution in case you had some problems. So we first, of course, look at our rho of t, which we know is e to the minus I h t times rho 0 times e to the I h t. And we can simply put in the Hamiltonian, which would be e to the minus I omega 0 I z t times rho 0 e to the I omega 0 I z t. And we also have rho 0 equals Ix. So we can write down everything in the corresponding matrices. Iz is a diagonal matrix, so we can directly use the fact that we can put in a diagonal matrix the matrix exponential into the coefficient exponentials. So we have here e to the minus I omega 0 t half as an element, 0, 0, e to the plus I omega 0 t half, then times the matrix Ix, 0, 1 half, 1 half, 0, and then again complex conjugate matrix, which is e to the I omega 0 times half, 0, 0, e to the minus I omega 0 t half. Now we calculate, we take the last two matrices, then we have the I minus I omega 0 t half, 0, 0, e to the I omega 0 t half times 1 half times 0 e to the I omega 0 t half minus e to the I omega 0 t half 0. And this is nothing else but 1 half 0 e to the minus I omega 0 t e to the I omega 0 t 0. And if you now calculate the trace, then the x is the trace of Ix dagger times rho, which is the trace of 1 half 0, 1, 1, 0 times 1 half 0 e to the minus I omega t 0 t e to the I omega 0 t 0. And this is 1/4 trace of e to the I omega 0 t 0, 0 e to the I omega 0 t. So we see the trace here is simply then 1/4 e to the I omega 0 t plus e to the minus I omega 0 t. And when we look at trigonometric functions, then we see that this corresponds directly to 1 half cosine of omega 0 t. No, actually it's not true. Minus here. Because it's switching. Yeah, matrix product. So yeah, and we can do the same for I1y, where we end up with 1 half sine omega 0t and Iz results in 0. And this is the same result, of course, that we had with the simple wave function calculation, just this time using the spin density operators. And this calculation even fits nicely on one page as compared to several pages in the previous calculation. So I personally find it more easy, and you just learned how to apply this operator. And if you put this in a computer program, then of course we can calculate essentially any spin time evolution for coherences and polarizations, just excluding relaxation. And in the following, we will see how we expand the basis into both the whole spin system so that we really can also calculate spin couplings and not only single spins.